In this video, I'm going to show you how to use the limits we were finding in the previous to graph rational functions. So this really should be kind of a review coming off 171 or pre-calculus algebra, but just to make sure we're comfortable putting it all together. So last video we talked about finding these asymptotes, the horizontal and vertical. And so for instance here we can see that we think the vertical asymptote is going to be at x is equal to 3, but let's show that. So the way we can show that is by taking the limit as x goes to 3, and I do want to specify from left to right, 1 over x minus 3. And that limit, as we come at 3 from the right, those would be a positive value, and so this thing would be going to the positive infinity. Now, that is good enough to state for certain that we have a vertical asymptote at x is equal to 3. But if I'm thinking about the graph, great, as we come at 3 from the right, it's going to go up. So we know that that is our vertical asymptote. I don't know what it's doing from the left. And so even though we only need to show one direction to find that we have a vertical asymptote, it can sometimes be helpful to find what's going on the other side. So again, just that first step was enough to state for certain that we had a vertical asymptote at x is equal to 3. By coming at 3 from the left, we can now see what we're doing on the other side of that asymptote. We're going down over there. So this is something we kind of took for granted a little bit in pre-calculus, where we said they should alternate with a couple exceptions based on the multiplicity of the asymptote, or multiplicity of the degree of the multiplicity of the zero that the asymptote kind of derived from. But now we can kind of see that more concretely. We can see that we're going down on both on the left side of the asymptote, going up on the right hand side. The other thing I might want to find is my horizontal asymptote. So to do that, I'm going to look at the limit as x goes to infinity. So as x is going to infinity here, this thing is going to 0. So we know that 0 is a horizontal asymptote, so we can complete our graph like so. Let's take a slightly more complex function. Let's call it g of x equal to x plus 1 over x squared plus 3x minus 4. And here it would definitely help to start by factoring the denominator. So if I factor the denominator, I'd have x plus a 4, x minus a 1. And so I'm going to take a guess here that my vertical asymptote is at -4 and at +1. And so to show that, I'm going to take a limit. But as x goes to -4 from, we'll start with the right, x plus 1 over x plus 4, x minus 1. So I'm going through these limits fairly quickly just because this is what we'd done in the last video. That's going to infinity. Already I've proven that I have an asymptote there, but let's just find what it's doing on the left-hand side. And so if we come at it from the left, we're going to get the negative infinity. So we now know what's going on at 4, and we know that there is a vertical asymptote at x is equal to 4. Take a limit as x goes to 1 from, let me double check those as I come at 4 from the left. That'd be positive. Yeah, that's right. And so then if we come at 1 from the right, minus 1. We'd have a positive. This would also be a positive, so that is going to positive infinity. And if we were to look at 1 from the left, x plus 1, x plus 4, x minus 1, there we're going to have that negative sitting in this position, and so we get negative infinity for that one. So we have a vertical asymptote at x equals 1. More importantly, that was a -4 on the top one, -4 and then a positive 1. More importantly, we now know the directions too. So we can do our graph at 1. We know that from the right, that was the positive, so it's going up there. From the left, it's going down. And then at -4, from the right, we know that it's going up from the right, and it's going down to the left. And then maybe I want to find my horizontal asymptote as well, so I'm going to take the limit as x goes to infinity, x plus 1 over x plus 4 times x minus 1. So that's going to 0. And so we know that these outer ones have to be going to 0, because remember rationals, even though we didn't prove it, we didn't find the limit as we go to the negative infinity here, the rational functions, it should be going to the same asymptote on both ends, so it will be going to 0 on both sides. We have the horizontal asymptote at y is equal to 0. But where we would have been a little bit uncertain is in the middle, right? The middle, there's any number of things that could be going on, but we don't have that uncertainty here because we have the ends. We know it has to cross in the middle somewhere, but we can connect it pretty easily. Now, one other thing that might be nice to get is to see exactly where it does pass through our x-axis. And so that's as simple as finding an x-intercept. To find the x-intercept, we set the function equal to 0. Well, the numerator is the only thing that's allowed to equal 0. And so we get x is equal to negative 1. So now I have a point. I know how we approach the asymptote on the left. We know how we approach the asymptote on the right. So there we have a pretty accurate picture. Let's take one more example. Let's take h of x equal to x plus 2 over x squared minus 4. First step, going to factor that denominator. And so we see that we have two things in the denominator that would make it 0, negative 2 and positive 2. However, the negative 2, I'm assuming that's going to be a whole, and we can prove that by taking the limit as x goes to negative 2. And we can specify left or right if we want to, but remember, if we're going to show something's non-asymptote, this is when we actually have to show both cases are not going to give us infinity. So we need to show both the right and the left. So the faster way of doing that is to show the two-sided limit, as long as the two-sided limit exists. So because those factors are the same, that's what led me to believe that it's going to be a whole. I can cancel them out. I'd have 1 over x minus 2. When we plug that negative 2 in, we get a negative 1/4. And so we now know that there is a whole at x is equal to negative 2, and we actually know the y value too. We know where it would have passed through. The whole is exactly precisely on the point negative 2, negative 1/4. So we actually have that point we can graph on our graph. Now, I believe that there should be a vertical asymptote at x is equal to 2, but to show that, let me start by finding the limit as x goes to, sorry, I said a negative 2, it should be the positive 2. X plus 2 over x plus 2 over x minus 2. If you want to use a simplified version, you could, but what we see is we get a 4 over 4 at times a 0. And so because the denominator is going to 0, this thing is going to infinity if we are coming from the right side. If we're coming from the left side, it would of course be the negative infinity. So let's show that as well. The limit is x goes to 2 from the left, x plus 2 x minus 2. Now, because we'd have values smaller than 2, we'd get a negative there, so we get the negative infinity. And finally, let's finish it off with a horizontal asymptote. Let's take the limit as x goes to infinity, x plus 2 over x plus 2, x minus 2. And that thing is going to 0. And so now we have everything we need to do our graph. We know that we have a vertical asymptote at, I didn't label these, let's say x is equal to 2. And then a horizontal at y is equal to 0. I know that on the right side of that 2, I'm going up. I know that on the left side, I'm going down. But what I've left out of this is that whole. So I've got to come back in here and say at negative 2, that y value would be negative 1/4. So right in there, that is going to be a whole. And notice I've marked it with an open dot. And now we have an accurate graph. We have our whole physically located at the position we found based on our limit. So there's the graph of our function. So we've done a few good examples here. We can do this with any number of asymptotes, any number of wholes. We may have slant asymptotes. We approach them the same way that we would do the horizontals. We would determine which way we're approaching those slant asymptotes, and we find those, of course, by doing our long division or our synthetic division. And once we have those, we just place them the same way.